Now let's consider a weak acid again. So as an example, I'll use the weak acid hydrogen fluoride, and it reacts with water, and it produces an equilibrium to produce H3O plus and F minus. So you'll notice the forward and reverse reactions. This is an equilibrium, and it has a Ka of 6.8 times 10 to the minus fourth. So what would happen if we just took F minus in a solution of pure water and put it in pure water? So now we have F minus, and it's in a solution of pure water. Well, it's going to react with water because water can be either an acid or a base. And F minus is participating in this equilibrium, but F minus can also react with water to produce HF plus OH minus. So we've seen water can be an acid or a base, and so F minus is missing a proton, so water could donate a proton to produce HF and the OH minus ion. And since it produces a basic solution, OH minus, F minus would be considered a weak base. Now, how do we know if this reaction actually goes or not? Well, we can look at the equilibrium constant of this reaction. And how do we find that? Well, we can use the HF reaction and the autoionization of water to calculate the equilibrium constant for this reaction. So let's look at the reverse of this reaction. And so the reverse of this reaction is 1 over Ka. Because I've written the reaction in the reverse, and now these were products, so now they're reactants, so I just flip the equilibrium constant. So I can write the autoionization of water and its equilibrium constant is Kw. So now, if I look at what cancels, 1 H2O cancels, H3O plus cancels, and the only thing I'm left with is F minus plus H2O giving HF plus OH minus. So the equilibrium constant for this reaction is equal to the product multiplying, if I add equations, I multiply their equilibrium constants. So this would be Kw times 1 over Ka. So numerically, that would be 10 to the minus 14th divided by 6.8 times 10 to the minus 4th. 1.5 times 10 to the minus 11th. So this is the equilibrium constant for this particular reaction, and since it's a base, we call it Kb. So it's a small equilibrium constant, so fluoride minus is not very basic, but it is a base in the sense that it will produce OH minus in solution. So now our nomenclature is we have an acid, this is water, and we produce the F minus ion, and we call this the conjugate base, since F minus is a base in solution. So if we have a general acid reaction for a weak acid. We have an acid and a conjugate base. So these are acid conjugate base pairs because the conjugate base is formed from the reaction of the acid with water. Now, how would we get F minus in solution by itself? Well, we can't just get F minus in the stockroom, but what we could do is get the salt of the conjugate base, say sodium fluoride. So I'll go to the stockroom and I'll get sodium fluoride. And it's a salt. And it will dissociate in water to give sodium plus and the fluoride minus ion. We already know that sodium plus from the first semester is a spectator ion. So it's neither an acid nor a base. It doesn't react. It just floats around in water as the sodium plus ion and watches what's happened. So that's why it's called a spectator ion. So this fluoride minus, though, is a conjugate base of HF. So if we take sodium fluoride in water, the equilibrium that will occur would be F minus reacting with water. Now, there's hardly any H3O plus in water. The concentration in pure water is 10 to the minus 7th molar. So there's not much H3O plus, so this reverse reaction is not that important. But what is important is, since there's water, pure water, there's a lot of it around in solution, so what is important is F minus reacting with the pure water. So this reaction can occur. So this equilibrium constant we saw is Kb, and it's 1.5 times 10 to the minus 11th. So say we have a solution of sodium fluoride and we want to calculate the pH. We would have to consider its dissociation, and then we'd have to consider the conjugate base reaction with water. And this is a base, and so a normal base reaction with water is the base. The water donates a proton to the base to form the H plus F minus. So now this is a neutral species, and the OH minus. So the charge balances, minus sign on each side of the equation. Okay, so if we want to calculate the pH, say we have, do an example. So we have 0.01 molar solution of sodium fluoride. What's the pH? Well, sodium fluoride's a salt. It will dissociate in water and produce sodium plus, a spectator ion, and F minus, which is the conjugate base to the weak acid HF. So the conjugate base will react in water just like a base does. So water is going to donate a proton to HF, to F minus. And so we'll have a positive charge and negative charge, so HF is neutral. And water, since it's donated an H plus, will end up with a negative charge, and what's left is OH minus. And we saw that this equilibrium constant is equal to 1.5 times 10 to the minus 11th. So let's calculate the pH. Well, Kb is equal to, we'll let X be, as before, the amount of OH minus formed. So HF is X, This would be initial minus x for F minus. So our equilibrium expression will be x times x over I minus x. Start to see a pattern here. X squared over I minus x. So we can use the quadratic formula to solve for x, which is the OH minus concentration. And if I do that, I will get 1.9 times 10 to the minus 7th for the OH minus concentration. So that means the pH will be, now I'll have to solve for the H3O plus concentration from the OH minus concentration through the autoionization of water as before. Gives me a pH of 7.3. So it's just very, very slightly basic because Kb is really small, 10 to the minus 11th.